Everyone. You can get started. Hello everyone, and a warm welcome to the third installment of the Fall 2022 Distinguished Team Seminar Series organized by the Department of Statistics at Purdue University. This seminar and the final seminar will be hybrid seminars. This year's theme is Recent Advances in Statistical Inference. A big shout out to the theme seminar committee for organizing this series. My name is Ontik Chakraborty. I'm an assistant professor in the department. We have a few announcements to make before we begin the seminar. This seminar series will be live streamed on our department's YouTube channel. The URL is www.youtube.com/c/Purdue University Statistics. Before we begin the seminar, we remind those of you watching on Zoom to please keep your microphones muted unless you are actively asking a question. If you are watching on YouTube, you can submit any questions you have in the chat and we will forward them to the speaker. Today, it is my pleasure to introduce our speaker, Professor Xiao-Li Meng from Harvard University. Professor Meng is the Whipple Jones Professor of Statistics and the founding editor-in-chief of Harvard Data Science Review. He is well known for his depth and breadth in research, his innovation and passion in pedagogy, his vision and effectiveness in administration, as well as for his engaging and entertaining style as a speaker and writer. Professor Meng was named the best statistician under the age of 40 by the Committee of Presidents of Statistical Societies in 2001, and he is the recipient of numerous awards and honors for more than 150 publications in at least a dozen theoretical and methodological areas, as well as in areas of pedagogy and professional development. He has delivered more than 400 research presentations and public speeches on these topics, and he is the author of the Excel Files, a thought-provoking and entertaining column in the IMS Bulletin. His research interests range from theoretical foundations of statistical inferences to statistical methods and computation to applications in natural, social, and medical sciences and engineering. Professor Meng received his BS in mathematics from Fudan University in 1982 and his PhD in statistics from Harvard in 1990. He was on the faculty of the University of Chicago from 1991 to 2001 before returning to Harvard, where he served as the chair of the Department of Statistics from 2004 to 2012 and the Dean of Graduate School of Arts and Sciences from 2012 to 2017. Today, Professor Meng is going to talk about miniaturizing data defect correlation, a versatile strategy for handling non-probability samples. We are honored to have Professor Meng joining us here today, and let's give him our full attention.
Thank you very much for that long introduction. And I thought I don't need an introduction, but that's fine. Well, I want to say that it's a true pleasure to be here. I know these days to deliver talk in person is not easy. I almost did not make it. So I'm happy to be here. And also thank you for giving me a chance to wear my tie and a suit. 3 years, this is sitting in the closet somewhere. I finally find that I can wear them again. So wonderful to be here. This talk actually really is a combination of 3 articles. See if I can do this. All right. And the most recent one, it could appear in the survey methodology. I was actually asked to be a discussant to discussing an article, an overview article about how to handle non-probability sample. I have to confess that when I was invited by the, when I was invited by the editor to write this discussion, I warned him. I said, well, this is a topic I have a lot to say. Just be prepared. My discussion might be longer than the original article. I think I probably succeeded. So So the article is available that if any of you interested, with this exact title, I'd be more than happy to send that to you. This work really started from back to my 2018 article, which actually work I started doing the whole thing about quantifying data quality. I started doing it back in 2012, so that was exact 10 years ago. And I've given many talks on the 2018 article. I want to see how many of you have heard me talk about the article before. All right, okay. I will test you how much you remember. Okay? But seriously, you will see that, and I'm repeating this article will be many more times because I do think there's a fundamental identity there. It should be remembered just like the bias trade-off. I'm offering an alternative way of thinking the bias issue. And it's particularly applicable when you don't have probability sample, right? And the one example I'm going to give actually was the article published last year in Nature, my first article in Nature. Hopefully it's not the last one. For those of you who have not published in Nature, Nature does torture you. Okay, it was a long process, but I appreciate that. I thought I was a very tough editor for Harvard Data Science Review. And when I see the Nature editor, my hands off to them. They really torture you. But it was great because scientific publication needs to be seriously scrutinized. These days, I have to say, we know certain cultures where there are way too many papers get published too fast. And I guess you know which one I'm referring to. I'm not going to mention names, but I think there's something to be learned from this Nature, these articles. What I want to talk about is really this notion of non-probability sample. Okay. Now, many of you probably have some ideas. What does non-probability sample refer to? And when I finished this discussion, I sent to my dear friend, colleague, Andrew Gelman. And he was so unhappy with me. He said, Xiao-Li, what are you talking about? There's no such thing as probability sample. All samples are non-probability sample. So he felt this notion of non-probability sample is redundant and offensive. With Andrew, right? He's very open. I think he's right. Well, let me actually think that really talk about, I think it's very important to be clear what do we mean by non-probability sample, because there are confusion here. And also, people would say statistics is all about probabilistic inference. What are you talking about when you talk about non-probability sample? Why statistician have anything to say about something non-probabilistic? So my point today is we actually have a lot to say about non-probability sample, but we need to be clear what do we mean by non-probability sample. So I know many of you like R. So we talk about statistical thinking with R, but not R you're thinking about. Okay. So the one thing is very important for those of us who working with missing data or any kind of sampling. So there is something called a reporting indicator or response indicator. That's the R I'm going to talk about. Okay. I'm going to talk about this R. It's a notation, but I say that in statistics, and I know many of you teach introductory statistical inference, we should teach this notion from day one, because this is the key thing, okay? The R is a very simple indicator. It's a binary indicator. The R simply says that if you're included in the sample, I equal to 1. If you're not, I equal to 0. Okay, how hard that would be, right? That's everything. But that thing, whether it's a random or not, that essentially coded all the kind of selection bias that get us into trouble. All right, so that is what I call statistical with R. I want you to read simple with R. You can call it reporting, responding, whatever you do, reporting, because there are many ways of thinking about. I also want to talk today really based on this thing, which I'm going to be very specific about. Traditionally, it's called a finite population calculation. All right. In this calculation, in this derivation, all the axes are fixed. Nothing random here at all. I'm not assuming they have normal. I'm not assuming they're anything. They're completely fixed. Okay. It's a little bit uncommon for most of us to think about axes being fixed, but that's what kind of a thing, right? It's a random. But here are axes not fixed. We're dealing with the finite population. All real-life problems are finite population. We have these so-called superpopulation models we are so familiar with, but these are conceptual extensions. Okay, they are incredibly useful. But we have to keep in mind what we really deal with in real life is always finite, no matter what problem you are dealing with. Okay, So here is the general setup. I'm assuming nothing's random, nor X nor R. Okay, everything can be random, can be fixed. And I think it's very important. This is the part of when I started writing this session, I realized that we probably need some kind of terminology or taxonomy about what we're talking about in terms of probability. So I propose we think about the three kinds of probability. One is called a design probability. Okay, design probability is a probability that is controlled and implemented by humans. Anytime you do sample design, that is a probability that you actually implement, right? You decide the random site, clinical bootstrap, clinical trials, differential privacy. This is a new topic. I know you have expertise here that you randomly inject noise into the data, okay? And also permutation test, Monte Carlos. These are the areas where we use a lot of probabilities, and these probabilities are N-O control. They are genuinely probabilities because we create them. Now, of course, a real computer scientist will tell me, Xiao-Li, there's no such thing but a genuinely probability because even these are pseudo-random generation. You know what I'm talking about, right? Nature has this kind of physical process, but at least those are, we know what we're doing. Hopefully, you're the one to create them. Okay. And this is what people, when we talk about non-probability sample, they basically talk about it's out of their control. When the people talk about non-probability sample, they really talk about non-design probability sample. It's not by design, okay? It doesn't mean probability is not there. Right? So this is, I hope this one is no controversy whatsoever because this one's quite clear, right? Okay, just say yes. All right. Okay. Now, the next one might be slightly harder, but I hope that we statisticians are also very, very familiar with it. I call it divine probability. You probably see where the word divine comes from, right? So these other probabilities are existing in nature or created by God, or we believe they exist. Okay? For example, when this R in and out, right? Now, when we have this, you get a sample. It's not by your control. It's by some observational study called inference. You have these R. Now, we typically need to assume that R is random. Well, it doesn't have to be random. Okay? The nature could be like every time we repeat a study, then we get exactly the same answer. It's possible. I have a strong opinion. No matter how many times you ask me, I'm not going to change my answer. Right? Okay? So, but what's important is you actually assume there is a probabilistic mechanism. You don't know what it is, but you assume that they're generated by some probabilistic mechanism. That itself actually is a big assumption. Now, many of us feel like everything in nature, in one way or the other, can be modeled by probabilistic model. That is absolutely not true. If you ever understand quantum physics, there are lots of phenomena that doesn't follow these rules. But even if you don't understand that, there are a lot of those things. There is a whole literature outside statistics called imprecise probability. So they feel the probability language is too strong to model the real phenomena. So they are slowly called there's more uncertainty than probability. All right, and it's a field I'm trying to get into a little bit because I find it fascinating. Okay, but the notion that something is random itself is actually an assumption. Okay, but we assume that all the time. For example, anytime you hear people talk about missing at random, my advice is to create that notion, right? Missing complete at random. You have to have a probability model before you can, not probability model, you have the probability construct in order to talk about that. Okay, so these are the kind of things what I call divine probability. Essentially, is you believe they exist, you don't know the specific form, but you need that notion. The one we use most, right, is what I call device probability, and that's the one we use all the time. For example, now we assume the probability including someone is a logistic. Okay, that's neither design probability because we never designed that way. Okay, nor possibly nature actually operate that way. We don't know. This is just a device we use to the inference. Because we find that's useful. It's an approximation, right? But I think conceptually it's very important to separate these notions and to know which one we're talking about. Okay? Is that clear what I'm trying to get at? Okay. What's surprising is to me, it's actually not surprising for people who actually work in this area, that you can dealing with non-property sample, you can go pretty far without even invoking any specific device property. So I'm going to focus on my 2018 article, was really trying to utilize this finite population calculation, exists naturally to push pretty far to measure the uncertainty. Measure these mechanisms, these two, these selection bias. And the most recent article I wrote about is it turned out that the identity I was using there really provides very good insight to a variety of methods out there. They're called quasi randomization methods, the superpopulation method. Some of you may have heard of something called it double robust method. But I'm going to show you that all these methods, once you understand that one formula, they all come out of that one formula very clearly. Okay, so essentially, it's a way to think about how do you deal with all these, basically the whole idea here is once you don't have the design property to make the selection, doing property sampling, do all sorts of stuff, your inference becomes much harder because it's not under your control, right? But there are all these methods essentially is trying to go back to create something that looks like design, design probability. That's kind of my opening to. I want to plant the seed in your mind that there's different probabilities. So be very clear when we talk about non-probability sample. Okay. All right, now I'm going to talk about this thing which I wrote in 2018. Now I know it's kind of obnoxious to call your own identity is fundamental identity, but we like to explain that. Number one, it is fundamental. I'm going to convince you. Okay, it's very important. Number two, it's not even mine. Okay, this was actually the initial version was in a 1954 Nature paper by Xiao-Li with the other guy named. They basically were using this to control the bias in the ratio estimate. My contribution is to realize that whole thing has a lot more substance in it, has a lot more can be dig out. And I also wrote it into the correlation version instead of covariance. You will see why that's important. Okay, so now I'm going to walk you through an incredibly simple derivation involving no assumption about anything being random, but I'm going to end up using all probabilistic calculations. That's because I'm using what I call the divine probability, something with given by nature. Okay, I have a population here, right? And let's say we want to estimate a mean. Now the mean doesn't have to be x itself; it could be function of the x. That's actually very general. Sometimes when you think about mean, people talk mean is just so restricted. Well, any moments, right? If you take an indicator function, then you pick CDF, everything. The only thing this does not include, which I'm working with on my students now, is that this does not include things like extreme order statistics, maximum, minimum, those things cannot be done in this framework. But otherwise, this carries me very far. Okay. Again, my emphasis here is don't think the x is random. I'm not assuming anything random, but I can write down what I want, that estimate, right? That's the population average. Anytime I see capital N, that's the population size. Okay. Now, the only trick in this whole thing is to write a sample average as a population average. Okay, actually, it's population ratio, right? So instead of writing the usual sample average, just average over the sample, you write them in terms of the population quantity, but you have this indicator. I equal to 1 is included, I equal to 0, it's not. So this expression is highly the same thing. Mathematically is mathematically is the same thing. And if you divide by capital N on both sides, well, actually, you don't even need to divide by capital N. Then this is just yeah.
Why you need to estimate?
I need to estimate. Population here is I don't know the population. I know there exists. For example, I want to study the
capital N. Yes, the population.
Right.
Who is there?
No, right, but you don't observe them, right? Let's say I want to study the United States population here. Okay, I know that's all the axes, but I have not observed them. I know that a finite population existed, and I want to study that population's population here. Right? It's like I'm sorry. No, I don't need the parameter notion at all. It's an estimate. I just want to know the population mean, for example, population average. Right? That's well defined.
So that's the target.
That's the target. Okay, right? Again, this whole finite population, this is all sampling literature. Say all the means, everything is a theoretical notion, but novel model, it's fine. Okay, we will eventually have that. But Dennis, the point is well taken. I don't assume the population is known. I just said, this is the population I want to study. Okay, and I want to study the population average, or population anything, any quantity of the population. Is that clear? It's just collection of numbers. I'm not attached to any property yet.
You mean know the population size at the level?
That is a great question. Conceptually, yes, but not necessarily I know it. Right? Because sometimes, for example, one great example is voting election coming, right? I want to know the whole voting population. Well, we don't know what the size exactly. We have some actually, in fact, estimating the population, voting population size in a hell of a work. Okay, but conceptually we agree there is, but you have to be careful conceptually because like any fixed time point there could be an end, right? The capital N itself could be estimate, could be a part of your estimate.
That then will inject some randomness in time in new little environment.
No, I don't have to, right? Just don't think about anything random. A finite population there. Right? There, just because something don't know, I'm going to take strict frequency perspective, right? Something don't know doesn't have to have a distribution on it. Right?
Why's question is, it's a great question, mine is not.
Yours was a great question too. Yes.
So you can find a population. You don't know the mechanism that's generated it. Maybe it was random, maybe it wasn't.
Yeah.
I'm going to tell you, you know what? I have a hypothesis for you. All of this was generated by the state uniform distribution. Because 1 over n based on each other. Now are you going to tell me whether my hypothesis is right or wrong?
I'm going to get you to that. That's a great point. Okay. You're absolutely correct. But now you see the problem with this crowd is you guys study too much statistics. In general, crowd, this will be very precise. Something fixed. The whole problem is moving toes on it.
Yes.
Now I need to undo you guys, okay? That's very, but actually, this is actually really, really great because think with me, okay? Because you will see it's important for us to have that language to communicate field outside statistics. The whole notion randomness is conceptually a mental block for us. Okay, I got myself into real trouble talking to one of my colleagues being engineer. I was telling him, thinking about this underlying distribution, whatever you have, think about the underlying distribution is generated, right? So don't you all take for granted. You look at me like I'm coming from some other planet and say, Xiao-Li, what are you talking about? Whatever I observe is what I have. What do you mean by there's an underlying population, right? See, but it's important to think about this way. But let me go on to show you how far we can go, even with everything is fixed. I'm not saying the necessary fixed. I'm just saying I'm not assuming it's random. It could be random. It could be generated by by something. Okay. Now this is the work essentially you already hit that, right? Because anytime I'm given a finite population, anytime you write down the mean is like that one, you can assume actually you're given a probability construct, which is put a uniform index for everyone. Okay? And if you think about that's all the probability we ever need to deal with. You think about it, it's really serious, right? Because anytime you have duplications, because there are some duplications, then it become non-uniform, right? If you were given the population, if you would not told anything about whether these X have any duplications, it's a uniform variable. If they have some X together, you got a frequency, right? Okay. So mathematically, it's very simple to write down that average, right? The difference between the sample mean, which I wrote that way, and the population mean, you write it in terms of the expectation in terms of this uniform indicator, right? Okay, that's just algebra. It looks a little bit scary, but for statisticians, this is the time when I started doing this thing, I realized, well, wait a minute. If you take the common denominator, the numerator is expectation product minus product expectation. What do you get? Covariance. When you have covariance, what do you do as statistician? Standardize it. Become correlation, right? So all I did is I take this exact error. This is an exact error, okay? Because there's no randomness whatsoever. This is just algebra, right? I can write down as the correlation, okay? The reason you get this middle part is because remember R here is 0, 1. It's just like the Bernoulli calculation. It's P times 1 minus P. Okay, so you get that, and then you need to standardize by the variance of the G so that you get the standard deviation. So these are just standard statistics, right? Very simple notion: correlation, covariance, mean, and the variance and the sample size. There's a simple linear algebra. I make no assumption except for one hidden one. I'm going to tell you in a minute, but this is the starting point. I'm going to tell you what each term means and why do I write this way and how much I'm getting out of this. Okay? But all I did so far is writing an exact error in 3 terms. Okay? Now, I want to emphasize one thing before I explain this. For this crowd, you probably see what's going on. These 3 quantities, remember there's an R and a G. Now they're actually random because index is random, right? Okay? Because index, the share is random, so there's correlation between them, well defined, right? It's all algebra. You notice that this is a characteristic of the G only. That's about the population, whatever the population you're in. This quantity is entirely determined the N and R. This entirely defined by the margin distribution of R only. That's the sampling aspect or the reporting aspect. And this is about the joint behavior, it's a correlation. Okay? Anytime you have a joint distribution, right? You have R and G. The 3 parts is the parts of G, parts of R, parts define the joint time. No, the only thing that the random here is the uniform on the index. This is just algebra. Yes, what I'm saying, the probability is entirely determined by the uniform outlet on index. No, there's not because it's not a property of X, it's not a property of R. It's probably index. But just think you have a pair, right? In the population, when I have a pair, just think about them as a sample, right? You can define the sample mean, sample variance, sample correlation. That's all I'm doing. Well, the average is that the average is just that population mean, right? You see, I wrote for this audience, I'm using this probability notion. Otherwise, I can just write it as average, just write it on algebra, right? It's a sum, it's divided by something. It's like because it's finite population. The reason I write this is to remind you that anytime you have a finite population, which is all the time, you can always do probability calculation, right? Because each one is equal chance.
Yeah, I'm not wondering the usual concept of CPD.
No, there's nothing good because I'm being very explicit. That's what I'm saying. That's what I call. Make sure you understand there's 3 different kind of probabilities. Right? This is what I call it. It was a given. It was a given probability. A person doing algebra does not even need to recognize these expectations. They could just write these terms because all I'm doing is just write down as the sum, right? But this is a sum. You can replace everything by the sum. Then you do this thing. Then it's like a finite. It's like finite population sample calculation, right? Except that you're thinking about your finite population is the entire sample you have. If you want to do that way. Is that? Yeah. Yes.
So if R is as the weight of the component sampling, I know that the first, the second, you brought was useful. What about the third one? Meaning you get the correlation of important weight and G.
Well, it will be coming later. Yes, you're right. But I'm giving this. This is saying this is the most basic version, right? Later we'll talk about why do you introduce weights. You want to reduce this, right? So everything coming, but I want people to recognize just at a very basic level. Nothing assume anything being random, other than just using this fact, mathematical fact, right? Basically, it's saying the probability, you don't have to think about the mechanism generator whatsoever. Conceptually, anytime, this is my current understanding. Probability distribution, you can just think of them as a mathematical tool for bookkeeping. A probability distribution to tell you for finite population, it's a way to tell you what the population is. Right? Because if the state can be every one and in 1 over n, the capital N is a term of size. Okay, so you can think about probability distribution as a mathematical tool to define a collection of of people. But now let me I'm grateful for this discussion because most places people say, well, that's kind of obvious, but for statisticians it's not, right? Because there's things you have to think through. But now let me show you the consequences of thinking this way. Why do I write this in 3 terms? Okay. So as I said, the difference is the exact error. Now, the first one, the correlation between R and the G, and I call that is the index for the data quality. So what do I mean by that? Well, what I just gave you is a mathematical expression. It says it's a finite population correlation. That everybody has R and has G, right? Whether you can include or not. So everybody has a pair, and you can look at the correlation among this whole population, right? As a pair. Okay. So, but this tells you that if the correlation is 0 or close to 0, then the error will be very small. Okay. So you can see. And the reason I call it this one measure data quality is because this one captures the selection bias. Basically, it says if the R, if you can include or not, depends on the value you're estimating, you're in trouble. The probabilistic sampling does what? I can show you in a minute. The probabilistic sampling is going to inject a randomness to R to ensure that, say, our average is 0. Because whether you're including the sample or not, it's by another random device, not by your own, say, well, I don't like people to know that I'm voting for Trump, therefore I'm not reporting, right? And that was how we got into trouble in 2016, right? Okay, so basically the probabilistic sample, I'm going to show you fundamentally what this probabilistic sample does, is to inject randomness into R, such that this practically is 0, regardless of which G you're looking at. Okay, so that is the qualitative measure. How representative? Rho here is measuring how representative your sample is in the population. All right, as long as the rho is 0, close to 0, you don't have to do probability sampling. There may be some other way to drive the same, first.
I'm trying to understand if rho is
That's a very good point. Yeah. Later I would call this data defect index. Right. Okay. But as a general term, I'm sorry, you're absolutely right. But these things have a different sign. The larger, the worse. Yeah. Yeah. The reason I call that is the next quantity is purely a quantity, it's a data quantity measure. Or actually, you should call it data sparsity measure. So that one is very typical as well, right? If the little n, which is how many in your sample, if the little n equal to capital N, then you have no error. Now I do make one assumption here. I'm making an assumption that everyone in your sample also comes from a population you want to study. Okay? It seems quite trivial in that algebra, but that's actually a fundamental assumption because in real life surveys, for example, when you're doing election pool surveys, you might be selecting people who are not eligible voters. Or they're measurement errors, right? So I'm not including those, okay? And then basically saying whatever the X you have, if you got it, it's from the same population and the value is correct. There's an additional version with the measurement errors, that can be handled, but that's a separate story. But that quantity is very clear, right? That quantity is driven by data quantity because it's also very interesting, right? If the little n equal to 0, it will blow up because tell you there's nothing for you to estimate, right? So this is essentially quantity control the data. This is controlled by the data quantity. The last one is just simple standard deviation, but I think for the general audience, I call it probability. So that's a fundamental characteristic of a population. That's measures in how homogeneous the population is. Remember, we're trying to estimate the population mean, population average. If everyone is all homogeneous, everybody is equal, all I need is just one sample. So you can see the errors have to be proportional to that. That's a well-known that sigma over n, right? So that part is like one is determined by the problem you're working on, one's determined by how many people, how many sample you have, but the most important quantity this formula tells you is that correlation. That correlation is driving to all the representative, that kind of sample. But so far, again, I have said nothing about it being random. Nor actually this exact formula. Okay. Later, we can inject a randomness to R, right? So you can do that. Okay. So again, I want to emphasize that nothing is assumed to be assumed random, only using the divine property R. The only assumption, as I mentioned, which is important, the sample xi are in the target population. Now I want to make yes.
So looking at the top formula, it seems like if the correlation could be 0, we would have no error, but somehow that seems counterintuitive.
Well, there's nothing. You're right, because this exact set. In order to estimate the mean and bias rate, all you need is to make sure that if you want to be exactly 0, that if the correlation is exactly 0, it will be 0. Because you're saying that this is very interesting, right? Basically saying that if the correlation is exactly 0, that means you have created a sample, which is the perfect miniature of the population. And therefore, that's possible, right? That I create a perfect miniature for estimating the mean. I'm not talking about estimating the okay. Now, I know everybody's familiar with the means, the bias variance trade-off formula. I want to make a comparison here, but I'm writing the mean square error terms not in the square term, but in terms of the exact, because this is the one eventually going to give us mean square error, all right? Because you square it and then you take expectation. But I want to point out in this formulation, it's obviously right. You minus plus something. You do need to assume there's a distribution for R. Okay, that's a different probability, right? R could be random or could not be random, right? If you have something about R, okay. So now, but the difference between these are two obviously mathematical because they're decomposing the same difference. They're obviously identical, but they have different meanings. The bias variance, a typical bias variance trade-off tells you there is a bias. Okay, this is what I call using a genetic language. I would say it's like a phenotype of formula. Tell you there's a problem. Okay, but not tell you where the problem comes from. It says there's bias. All right, that the multiplicative decomposition tells you what the problem comes from that correlation. Is that correct? Okay, so basically the multiplicative tell you there's 3 ways to drive the error to be large, right? Not have enough sample, the problem is difficult, and your sample is not representative. If you can make any one of them equal to 0, you're done. If the population is entirely homogeneous, as long as n equal to 1, it's a 0, right? We're done. If you have everybody in the sample, in the population is in your sample, assuming no measurement error, you're done. The one least intuitive, which we haven't solved, is exactly point out. If you get the correlation equal to 0, you're done too. Because now you have a perfect miniature for the population. Okay, and but here is the fun part, right? What we statisticians have been doing is now we're going to assume all kinds of models about this R. Statistical matching, all kinds of stuff is coming from this R. We're going to make assumptions. If I really have a randomized device, I use whatever the random sample tells me. If I don't, I start to make up assumptions. So just stick with something in control, so on and so forth, right? But so that comes into that, and I'm going to show you how all these formulas, all these different methods eventually can be all summarized by the one formula, which is not surprising because they're completely identical. Okay, but the advantage of the multiplicative one shows what are the factors can lead to large error, but it also is exact that it's a base to start. From there, you can square it. Whenever you have distribution of R, you have X, you can, on top of it, you do whatever you want. Okay. And I'm going to show you that what that would lead to. All right. So the one thing that's going to be a little bit surprising later by doing this, you will see once we take into account the quality of the population, the quality of my sample, it turns out that you may have a huge big data set. It turns out to be your sample size, the effective sample size will be very, very small. But in order to understand that, I think it's useful to remind ourselves that why we can ignore the population size, right? For all all the courses you have taught, I doubt anyone is teaching the student to pay attention to the population size. We always said ignore that capital N. The only time you don't ignore it is if the capital N is small enough, your population is close, right? And you have a finite population correction. Anybody who don't understand the statistics will find this completely bizarre. How could the problem become easier when my population gets larger? Shouldn't that be harder? Right? It is harder. The reason that we can do that away is because we made a really strong assumption. Now, I always use this to illustrate, particularly for now-six audience. I think for this one, you guys probably don't need me to do this, but nevertheless, I'm doing it anyway because I want to remind ourselves how crucial this assumption is, right? So the best analogy, one of the best analogies about this soup, I found these a tiny, cute mini soup, and I got a gigantic bucket soup, right? We all understand that if you are asked to test how good or how bad the soup is, all you need to do is steal them well and take a 1 spoon or 2. That's all you need to do, right? You never really say, okay, now this big bucket, I need to drink half bucket in order to really understand that, right? Okay, so now here's the part, right? So the whole idea is because you want something to be homogeneous, right? When it's homogeneous, a small sample is all you need. In real life, you cannot really mix the population. So what we do is statistically speaking, the randomization, right? The idea is to have everybody have an equal chance. But the fundamental assumption, which you all understand, right? We probabilistically we call it IED because single random sample, we call equal probability sample, is all about when we can stir well. My question here is when do we fail that? When do we fail it? How terrible the problem will be? Well, we all understand that. Many of us have written articles about the things not probabilistic, have bias, and so forth. But I really want people to pay attention here because it turned out to be really far more damaging than we realized. Than I have realized. There's something you have to keep in mind. There's actually a physical reason for that. Look at these 2 buckets of soup. Stir a small soup is pretty easy. Stir a big soup is much harder. In fact, because there's nothing about the size of the container, it could be the entire ocean, right? Think about how you're going to stir the entire ocean. But the moment that you assume it's a random sample, you assume the problem away. You assume that I have stirred, whether it's a small soup or the whole population, I've stirred exactly the same way. That's where you kill the capital N. You assume that it's away. It's there, right? And that is the fundamental assumption. The probability assumption, probability is wonderful because I had the power to really kill this thing, right? Okay, so now think about this. So I want to show you, okay, now what I'm doing is the formula I have, right? I'm going to rewrite the formula, and this is the Z. Remember, there's a difference is these quantity multiplied by this. I'm just re-standardize them using this simple random sample standard deviation. That's a probability, that's a Z score, right? Okay. So what I'm showing you is this. Suppose the R was a simple random sample. Okay. If that was we don't have to worry about more complicated stratifying cluster, but think about the simplest one. If it is simple random sample, the Z can be written now as no time disturbed n minus 1. That's just directly from the formula. If it is a single random sample, what's going to happen is the variance of the Z, because I standardize this way, the variance of Z is one. Therefore, you can see that if you have a single random sample, that correlation, it has mean 0, and it has a variance is 1 over capital N minus 1. It's very precise, okay? That means that if you have single random sample, then we know just by doing and these are normal approximation here works so well, because capital N is so large. Right? You're practically guaranteed that no matter how you do it, that rho is practically 0, right? It's a point quantity, okay? It's a time quantity. So what that says, if you have a single random sample, or actually any probabilistic sample, you're guaranteed that rho. Remember, this is a population correlation, right? That's your sample. Population correlation, the finite probability correlation is practically 0 regardless of the G is. And that delivers the representativeness by doing the probability sample. But look at this, what happens if you don't, right? So see, here is the magic, right? So what happens, I just show you the rho with probability sample is on the order of 1 observed capital N. The middle part is square root of capital N. It is that cancellation. Get rid of the capital N. The correct? All the wonderful probability sampling gets us to the word do is because this guy cancels with this guy. Now the trouble here is that once this guy is not controlled by probability sample, for example, it's a self-reported, a social media number. No matter how small this is, as long as it's not on this order, it's going to be multiplied by this guy, it's going to blow up. It's going to blow up in a huge way. Because it has square root of capital N. Typically, the little n means nothing compared to the capital N. Right? Now you see why this probability sample is so important. The probability sample fundamentally control that correlation. And it controlling it this way that in the population, 1 over square root of capital N, not 1 over square root of N. Okay, so that's the fundamental reasons why the probability sampling works so well. On the other hand, the trouble now we have is we no longer have design probability to control the sky. This is going to be in the wild. And I said I'm just scaring you because it's going to multiply by capital N. And this is what I've been calling, and I will show you the real results. I call the law of large population. The larger the population, the worse thing will be because you're multiplying by the capital square root of capital. Okay. So now we're going to give you the. Is this part clear? What I'm getting to. Okay. See, so far I have not made any assumption about anything being random, other than just using that divine probability, what I call. Okay. And it turned out this law had a real, a real meaning even in the classical statistics. So this is what I call this rho. I call the design defect correlation. To answer to the question, it's a defect, so it's larger. It works. Okay. I also call something called a data defect index, which is the square root, expected square root of that. And this is the R here is whatever random mechanism you have. If you don't, take it as a singleton, right? So the traditional design effect is defined as the variance of your design compared to the variance of single random sample. Okay. Here I could extend the notion instead of talking about variance, I talk about the square error. So we talk negative bias sample. Okay, and it turned out that this is what I called this design data defect index is simply the design effect divided by by capital N. So this is a complete trivial result in the functionality of the really mathematical trivial, but it tells us how important it is to understand this, right? Basically, what it said, for single random sampling, this data defect is had to be 1 over n minus 1, and you can prove very trivially in order for this thing to stay the usual 1 over square root n answer, right? Probability sampling, the di will have to be on the 1 over n thing, and so this is the trivial result. Almost this expression, but it's fundamentally tells you what's really going on, right? In order for explanation error to be 1 over n, you have to have what I call the data defect, the index to be 1 over capital N. That's if and only if it's not 1 over capital N, you're not going to get a 1 over n results. Okay, because the only way you can get it is you have to cancel the capital N. Otherwise, things are going to be different. Right? Only 10? I thought I have 10 hours. Okay, so sure. The deep trouble, which is we always use the word deep learning, deep substance. That's called deep trouble. The deep trouble we have is whenever it's dn, the data defect impact, which is like a rho square, if it does not vanish with the 1 over n, or when the correlation does not vanish with the square root of 1 over n, then we essentially have all these terrible values. Okay, since I only have 10 minutes, I certainly will skip certain things. But let me see. Okay. So let me first tell you like the devastating impact of this, right? What I call is how small is what big data. You can write down using the formula, right? And I have super random sample, I have this formula. You can write and say, what will be if I know there is a defect, what will be the equivalent of sample size from a single random sample deliver the same mean square? So you can equate that. And you can write down what is that what is that effective sample size will be. And if you look at what sample size it will be, it's quite trivial. You know, this is the exact expression because this need to make sure if this thing really equal to 1 over n minus 1, it would deliver the capital N. Otherwise, you can do this approximation. But there are two things that's very important to notice. First is that the effective sample size does not depend on little n. It depends on the fraction of it's a relative size. Okay, so it says what matters is not how large your sample is. It's what's the fraction in the population. You see, the population size comes in. That's the troublemaker, right? Number 2, you see the rule is essentially is 1 over that rule squared. Okay, so that's a smaller rule, the larger your effective sample size will be. But look at how bad this thing will be, right? So, so why do we do random testing? This was a little exercise done by Walter Dempsey from Michigan, biostat. I mean, I'll tell you why he was doing this in a minute. But he said, well, let's go through using this formula. Let's go through the following exercise. Think about we do random testing for the COVID. We want to estimate how many people in the population will be tested positive. Okay. And he said, well, take New York State, which has about 20 million people, and let's say that we took a sample with 10,000. In most studies, 10,000 looks pretty big, right? Okay, 10,000. So it's 1 out, and the rate is 1 out of 2,000. Now we know that at least early on, it's probably continuing the case. You don't test people randomly. You test people because they start developing symptoms, they have some exposure. You worry they are the ones going to be positive. So that right there, you see the correlation, right? You know the population you're going to test it is more likely going to be positive than the one in general. Well, let's assume that correlation micro is 0.5%. That seems should be pretty small, right? Let's assume that not even 5%. Let's assume that thing is 0.5%. If you assume the 0.5%, plug the formula, you see what's effective sample size? 20. You test the 10,000. That 0.5% correlation, not 5%, 0.5% correlation. Kills it. You end up with the sample size essentially 20. I just want to use this, this example to say, look, we really have to pay attention. And if you know that that's not surprising because when you have this large sample, what happened? Bias variance. Variance is entirely minuscule. It's all the bias data. You know how hard it is to compute the bias? I mean, this.
Sorry, we have a class now.
Okay, we'll be done. All right. Well, maybe the class will join us. So, well, let me just because of time, I'm just going to show you enough done. I'm going to invite you back to the real talk. This was from the Nature article. There are these 3 different surveys: Facebook, Census, actually Ipsos. Facebook had 250,000 people per week. Census Bureau had 75,000 per week. Actually, 1,000. CDC benchmark. What you see there, the larger the sample size, the further away from the CDC benchmark. Okay, I'm not going to get into it, but it's quite easy to understand what's happening here. Facebook only surveyed the Facebook users. The Facebook users are much more highly educated.
Look, I have 50 people.
Yes. Okay, I'm done. Thank you. All right. Done.
Thank you very much for coming. Xiao-Li has been really working very hard to make this thing. He actually arrived at 2 a.m. this morning. Working very hard for us. And I was able to thank Xiao-Li and able to sit in for picnic tomorrow. So if I want to talk more, to stand with you tomorrow picnic. Come to picnic.
Right. Now I understand why you need to be here.
Thank you all of you.
Thank you.
See you all next week.